In this video, we're going to be tackling some complex rotational dynamics problems. So let's start off with question 1. You will need to be able to use conservation of energy to solve rotational dynamics problems. You are given this picture. A solid cylinder is released to roll down a hill. What is the moment of inertia equation of a cylinder? So what we know is that the moment of inertia of a solid cylinder, this is always going to be I is equal to 1/2 mr squared. Now, after this, what would be the conservation of energy equation to solve this shape? So, conservation of energy. Well, we can examine this. So we know that at the top, you only have potential energy because you're up there. And potential energy, aka U, is just equal to mgh. And then we know at the bottom, we know that it was rolling down a hill. So if it was rolling down a hill, that means finally EF, you have both translational and you also have rotational because of it was rotating to get down the hill, and it was also moving linearly in a line. So you have both the translational and the rotational motion. So to represent this, we can write that our EF is equal to kinetic energy and also the rotational kinetic energy, KE rotational and trans. So just all kinetic energy maximum down here. Basically, you can write this as the respective formulas: 1/2 mv squared plus 1/2 moment of inertia omega squared. And we can use energy conservation. Energy conservation, because there's no friction, we can assume that there's no friction because of the fact that we can use conservation of energy. And in conservation of energy, we know that the system, it starts out with the initial amount of energy that you have in the system is going to be equal to the final amount of energy that you have in the system. It's only going to be converted to a different form, and we know which forms it converted from. It converted from potential energy to kinetic energy at the bottom, just in different forms. So that's going to be equal to the potential energy is equal to all of the kinetic energy. So that's going to be equal to mgh, which we had up there, and 1/2 mv squared plus 1/2 the moment of inertia omega squared. And we know that because it rolls without slipping, there's a condition for rolling without slipping, and it's this. So this is the condition is that omega is going to be equal to your angular velocity is equal to your translational velocity divided by the r. So now we want to solve symbolically for the cylinder's velocity. So we know that we can substitute I is equal to 1/2 mr squared. And we also know up here we had this relationship, the rolling without slipping relationship, which is this. And we can bring this down here actually too, because we're going to use this. And we have our our conservation of energy equation up there. So we're going to write mgh is equal to 1/2 of mv squared plus 1/2 this was here, so this is going to be just moment of inertia there, so that's going to be 1/2 times 1/2 mr squared. So it's going to be this, and that's times the omega, and we know that omega is defined as v over r. So that's the rolling without slipping equation, so we can use that. That's v over r, and then that's just here. Now after this, you can simplify the rotational term. So this is actually squared. So v squared, that's going to be v squared over r squared. So we can sub that back in. So that's, and then if you multiply these, that's going to be, okay, we'll just rewrite the whole thing, mv squared plus 1/2 times v squared. 1/2 of mr squared times v squared over r squared. Might as well it's okay, we can just get rid of that. And then after this, we can cancel out the r squared because we see both of those there. And then after this, we can just multiply. So this is going to be equal to 1/4 mv squared because you can multiply those twos. And then you have 1/2 mv squared still over here. And then after this, you still have this is all equal to mgh. And then after this, you can combine the 1/2 and 1/4. That's going to be 3 over 4 mv squared, and that's equal to mgh. Now we can see that we have mass on both sides. So if you divided by both sides by m, you would have seen that the mass cancels out, but we can just cancel that out. It's just algebra. And then after this, we have gh is equal to 3 over 4 v squared. So then v squared, if you multiply by the reciprocal onto both sides, then you have that cancels out. And then you have that cancels out. So then you have on this side, v squared is going to equal to 4 over 3 times gh. So v, if you take the root of both sides, then you're just going to have that v is just equal to the root of 4 over 3 times gh. And that is your answer for that part. Now, okay, there are two people pushing on a merry-go-round or against each other. It starts from rest. Calculate the torque for each force shown in the picture and give directions. So we can see that we have this picture up here, and they're pushing each other. So we know that the torque is, okay, what do we want to find? Oh, the torque. Yes. So the torque formula is going to be equal to RF sine of theta. So we know that the first force, so our first force, I don't know, it's not given here, but it's okay. So our first force is going to be 25 newtons. So that means torque 1 is going to be equal to 0.50 times 25 times sine of 30 degrees. So that's going to equal to 12.5 times 0.5, and that's going to equal to 6.25. And then this is going to be newtons times meters, and this is actually going to be counterclockwise. Now, that's just for our first force. We also have to do our second force. So for our second force, that's going to be 35 newtons. So that means our torque 2 is going to be equal to 0.70 times 35 times the sine of 60 degrees. And that's going to equal to 24.5 times 0.866. So that's going to equal to 21.2. And then it's actually going to be that the direction is opposite. So that if the direction is opposite, this is actually going to equal to negative 21 n dot m. Now, after this, we have to find our net torque. So for, oh, sorry, this was our photo right here. 25 newtons. And we have, over here, we have 35 newtons. Yes, that's where we get our angles. So now, for our net torque, this is going to be equal to 6.3 minus 21, and that's going to equal to negative 14.7. That's approximately going to be negative 15 newtons times meters. And now for rotational acceleration, we know that the relationship that encapsulates rotational acceleration is going to be in torque is equal to the moment of inertia times the angular acceleration. So if you solve for angular acceleration, that's just going to equal to the torque divided by the moment of inertia. That's going to equal to negative 15 divided by 20, and that's going to equal to negative 0.75 rad per second squared. So that's going to be just this. What is the angular displacement and linear distance traveled after 2 seconds if it has a 2 meter distance? So after 2 seconds, we know that it starts from rest from earlier. So that means that the initial is just going to be equal to 0. So that we know that if it's that, then we know that the kinematics equation is going to simplify down to this. It's going to be theta is equal to 1/2 times angular acceleration times t squared. And that's going to be theta is equal to 1/2 of negative 0.75 times 2.0 squared, and then that's going to equal to negative 0.375 times 4. That's going to equal to negative 1.5 rad for your solution. And now, what is the rotational moment? Oh, okay. We want the linear distance traveled. So in order to relate this back to linear distance, that means that we have to do one more step, which is that we know that the sector R, the S, the sector is a sector of a circle is essentially just like the part of the circle that it traces at an angle. So an angle is covered, and however it takes for you to travel that angle on the circumference of the circle is going to be that sector of the circle. Now, the sector of the circle is equal to the radius times the angle that you're traveling. So we know that s is going to equal to 1.0, and then we know that our theta is going to be 1.5. So that means that s is going to equal to 1.5 m. What is the rotational momentum after 2 seconds? So in order to find the rotational momentum, we have to first find the angular velocity. So angular velocity is going to equal to omega, and that's going to be angular acceleration times t. And then if we plug in, we have angular acceleration is negative 0.75, and then time is in 2 seconds, so t is equal to 2.0. So then our time is just 2.0. That is going to equal to negative 1.5. And then for angular momentum, aka rotational momentum, that is going to be equal to L, and that's going to equal to moment of inertia times the angular velocity. That's going to be equal to 20 times negative 1.5, and that's going to be equal to negative 30 newtons dot m dot s. Now, that is going to be our answer for this. A golfer applies 50 newton meters of torque to his golf club. Assume the club is 1 meter long rod with mass 0.5 kilogram attached to a 0.5 kilogram head. What is the moment of inertia of the club? So it is a rod and a mass at the end. So we know that it's gonna be a rod. This is the rod, and then there's a mass at the end, and we want to find the moment of inertia of this. So we know that for a rod about one end, the formula is I rod is equal to 1/3 of the mass times the length squared. So I rod is going to be equal to 1/3. Our mass, our m, is going to be 0.50, and our L is 1.0, because this is, I'll actually mark this. So this is going to be equal to 1.0, and our club is 0.50 kilograms. Now after this simplifies down to 0.167. Now for a head, we're going to treat it as a point mass at the end. So at the end, the rod is this, and then the mass of this is also going to be 0.50 kilograms. So this is going to be I of the head is going to equal to mr squared for all point masses. So that is going to be equal to 0.50 times 1.0 squared. That's going to equal to 0.50. And now for the total, that's going to equal to 0.167 plus 0.50. That's going to equal to 0.67 kilograms times meter squared. What is the angular acceleration that, what is angular acceleration that this will create? So torque is equal to the moment of inertia times angular acceleration. So solving for angular acceleration, that's going to be equal to torque over moment of inertia. That's going to be 50 over 0.67. That's going to equal to 75 rad per second squared. Find what is the final speed of the club head. Assume that it spins 1/2 of the circle. So we know that 1/2 of a revolution, but we want it to go to theta. It has to be in terms of theta, and we know theta is going to be equal to pi rad. So then we know we can use the kinematics equation omega squared is equal to omega final squared is equal to omega initial squared plus 2 times angular acceleration times theta. So we know that it starts from rest. So if it starts from rest, that means that this is equal to 0. Starts from rest. Initially, it's not moving. I mean, initially it has no velocity. So that's going to be equal to omega squared, final squared, is equal to 2 times 75 times pi. Now, we have, this is equal to 150 pi. And we have omega f is equal to the root. Okay, take that. That's going to be the root of 150 pi. And that's going to equal to 21.7 rad per second. Now, we need to find the linear speed. So in order to go back to translation, we need to use that v is equal to r times omega. So the velocity is equal to 1.0 times 21.7. So it's just going to equal to 21 meters per second at last. Now, what is the final rotation energy of the golf club? Well, rotational energy is going to be equal to k 1/2 times the moment of inertia times omega squared. That's going to equal to 1/2 of a moment of inertia that we found was 0.67 in total up here. So if we plug that in here, 0.67, and we have our moment of inertia times omega squared, that we found, so that's going to be 150 pi. So this is going to be equal to 0.35335,471, and that's going to equal to 150 joules. Now, what is the final rotational momentum of the club? So angular acceleration is equal to moment of inertia times omega. So L is going to equal to 0.67, which we found, and omega we found, we know it's 21.67. V is this. We know that omega is equal to 21.7, which we found here, which we have here as well. And we know that L is equal to 14 kilograms dot m squared over s. A 1.53 kilogram mass hangs on a rope wrapped around a 66 centimeter radius, 7 kilogram disc-shaped pulley. What is the inertia of the disc pulley? So we know that the formula for the disc, inertia for the disc, is going to be I is equal to 1/2 mr squared. So then you're going to have I is equal to 1/2 of 7.0 times 0.66 squared. So that's going to equal to 3.5 times 0.4356. That's going to equal to 1.5 kilograms times meter squared. Now, what force does the hanging mass have? What torque does it apply around the pulley? So, we know that always that the weight is always going to equal to mg. So, we know that that's the mass was 1.53, and our gravitational constant 9.8. That's going to equal to 15 newtons. Now, if we solve for torque, we have torque is equal to R times F. That's going to be equal to 0.66 times 15 that we just found. And then that's going to equal to 9.9 newtons times meters. Now, what is the angular acceleration of the pulley and the linear acceleration of the mass? So we know that torque is equal to I, moment of inertia times angular acceleration. So angular acceleration is equal to torque divided by the moment of inertia. So angular acceleration is going to equal to 9.9 divided by 1.5. So that's going to equal to 6.6 rad per second squared. Now, in order to convert this to linear acceleration, you know that your linear acceleration is equal to the radius times the angular acceleration. So then your acceleration is going to equal to, plugging in 0.66 times 6.6. And then you're going to have that's equal to 4.3 meters per second squared for your A. Now, finally, how long does it take the mass to reach the floor if it is 1.5 meters below the starting point? So we can use the kinematics equation in translational, which is 1/2 at squared. So that's going to be equal to 1.5. So your displacement is 1.5. 1/2. And then your acceleration is going to be equal to 4.3. And then that's t squared. So that's going to be 2.15 t squared. And then that's equal to 1.5. So we want this t squared. So that's going to be t squared is equal to 1.5 divided by 2.15. T squared is going to equal to 0.698. And t is going to equal to the root of this. So t is going to equal to 0.84 seconds.